So thank you for that introduction. Thank you for the invitation. Thank you all for coming along. So I think Carolina asked me to speak about something to do with logic in industry. And that's not exactly what I know. I never worked doing this kind of thing in industry. But maybe I can say something. So I want to talk, and partly I'll talk about some research, but really I want to talk about how we think about what research is worth doing. And the obvious main answer and most important answer to that is individually. So, I mean, the premise of this workshop, like all of these mentoring workshops, is in some sense a bit strange. You have to decide for yourselves what research you think is worth doing and what's compelling enough to be worth your time and your effort. And in no sense could I or anyone else possibly dictate that. Maybe I can say something that will broaden the scope of things that you might imagine, or maybe it will just be interesting as a possible path. So here we are in a workshop attached to LIX. LIX, an international forum on theoretical and practical topics in computer science that relate to logic, broadly construed. And I have some fondness for LIX. My first paper was in LIX quite a long time ago. We'll come back to that a little bit later. But since then, I've not so often been here. I think Luca Catani and I had a paper in 2000 or 2001, and I haven't been back since. So from some point of view, I'm not the obvious speaker for a workshop like this, because I've taken a path sort of away from here, but maybe that path is still interesting to look at. If we look at LIX sort of in context, what do we see? So on one side, we have all of the world of maths, right? When you've left computer science. On the other side, like the nearest neighbor is what you might call the theory end of SIGPlan, the theory side of Popple and Fossax and that kind of thing. And then a bit further away from that, you have maybe the practice end of SIGPlan, people that do static analysis and that kind of thing. And then further off in the distance, there's the whole world of systems research. And here I'm, just for the sake of argument, I'm compressing an enormously complicated graph onto one two-dimensional line. So let's just pretend, even though it's false, that operating systems and computer architecture and security and networks are all the same thing, which of course they're not. And then a bit more practical still, there's people that do mainstream language implementation, like GCC compiler writers and industry architects and Linux kernel developers and standards committees for all kinds of things and so on. And then maybe more practical than those, you have the group of people that actually write straightforward-ish, non-systems code, back-end applications, let's say. And then maybe there are a still larger community of web developers, and then a still larger community of spreadsheet users, and then a still enormously large community of consumers. And an interesting thing about this line, I think, or about the graph really, is the diameter, right? If each of these steps is sort of the step from one person or one community thinking that the next one is very theoretical or very practical and almost someone you couldn't really talk to, then it's maybe a diameter 9 graph. That's pretty big. Each of these, on the whole, leaving aside the first, roughly speaking, each of the communities gets bigger as you go down. There are many, many, many more application developers than compiler implementers, let's say. Not sure if there are more of those than systems researchers, but if you add up all of the rest of these, then probably there are. Okay, so where have I been? So as I said, my first paper, it was in LIX. But then I've been gradually moving over my career into like the SIGPlan world and further into the SIGPlan world, and then touching the systems research world, and then touching the sort of standards committees and industry architects and Linux kernel developers. So this is a trajectory. I'm by no means unique in following a trajectory like this. I think it's quite interesting. It's arguably easier to follow a trajectory from theory to practice than the other way around, just given the way that our education works. It's hard to get a really solid grounding in logic and maths and semantics when you're starting off as a Linux kernel developer. It's hard to get a really solid grounding in Linux kernel development when you're starting off in logic, but it's not that hard to learn to talk to those people. We'll come back to that. I was going to say at the beginning, so this is not an enormously large group, and this I think can be quite an informal talk, and it can be kind of interactive. So if you have questions as we're going along, then just type them into the chat, and if I can, then I'll pay attention and we can talk about them. Okay, so what I'm going to do is just talk a little bit about this trajectory, not because it's the kind of thing that you should do, but just because it's a thing that one can do and that one might not have thought of. And I'll just pick out a few points. I think I probably won't have time to talk about all of these, but just a sample of different papers and projects, and talk a little bit about the motivational argument for each one and the kind of contribution for each one and the kinds of success and failure they might be, and sometimes the kinds of interaction one might have between theory and practice. And I'll do this like picking on my own papers because that lets me insult them and say bad things about them in a free way, which one doesn't often get to do. So this first paper, Linux 1994, bisimulation is not finitely, first order, equationally axiomatizable. So I was a PhD student with Robin Milner, bless him, and I think, I forget now, but I think he must have suggested that I work on this problem. He talked about various things. Some of them had gone somewhere, none of them had really gone anywhere. This ended up going at least to some kind of publishable theorem. And that's what it is. The main contribution is a theorem, and it's sort of straightforward to state. Right? And then actually not very hard to prove in retrospect, but the interest is in whether it's true and in the proof, rather than in creating a theorem that no one had ever thought of before, a statement that no one had ever thought of before. And then I claimed some motivation. I claimed, or the paper claims, that this kind of result gives you some insight into the equivalence, the bisimulation or trace equivalence or whatever, and the operators of the calculus, and that it lets one compare against a view that was sort of reasonably prevalent at the time, in which one defined calculi by giving just an axiomatic semantics off the bat. And I claimed that a sound set of axioms was useful for reasoning. So looking back on these, I mean, so these are of different kinds, these motivations. So the first two are sort of inward looking inwards towards the community of process calculus design, let's say, or process calculus semantics. And the last is looking outwards towards a community of people who might want to use sound systems of axioms for reasoning about actual concrete processes that they cared about, rather than for doing meta theory about processes. And that's an interesting kind of motivation, because it's appealing to a potentially larger community caring about the results, right? Like each of these communities, as I said, tends to get larger, and we're sort of conceptually sitting here at the moment and looking out to a potential community of people wanting to use this stuff for verification. And in fact, looking back, I mean, these two are certainly a bit dubious, but this one really was a bogus motivation. Right? As soon as you start having particular processes that you care about, say for describing some protocol or other, they get so large and so complicated that you're not, on the whole, doing equational reasoning about them. Right? You're doing other things, if anything. Yeah. So these motivations are also interesting because I think they were kind of standard. And one ought to be suspicious of standard motivations. Right? The fact that somebody else has written a paper about some topic is not a good reason for you to. The fact that someone else has claimed that something is a good motivation for doing something or other is not itself a good reason for you to believe it or to restate it. And in hindsight, probably I should not have claimed some of these. Was it a success? Well, sort of. I mean, it was a theorem. It's kind of interesting. People have cited it occasionally over the years. Has it really affected the world? Not so much. Okay, moving along. A couple of years later, as a postdoc, still with Robin, bless him, I wrote this paper about implementations of and semantics for concurrent language. And this within the context of PICT. PICT was a language invented by Benjamin Peirce, who was a postdoc in the same group at the time. And it was a programming language, but based on the pi calculus. And at the same time, so he and I talked about PICT a bit, and at the same time, there had been for quite a few years at that point, a whole literature about process calculus equivalences and different equivalences and different congruences and discussions about which was good and which was bad and which was right and which was wrong. And this I found all rather frustrating. And my hope was that if one looked at not at process calculi in the abstract, but at them reified in some particular usage context, then actually that context would tell you what mattered, what equivalence was appropriate, or what congruence was appropriate. So in this paper, I set out to do that, to look at this particular usage case of the pi calculus and see if one could tell or argue convincingly that one equivalence rather than another was actually appropriate for use for reasoning about programs. So there is a theorem in the paper, but that's not really the main point. The main point is this argument. Did it have any impact on anybody else? As far as I know, no. But it was certainly valuable for me. Right? So this is, in some sense, when I started thinking about the relationships between our mathematical models and the real systems that they're supposed to model. Well, some of them are supposed to model. Okay, moving along a bit later. So around 1999, Jan Vitek, who I think then was a postdoc in Geneva, and me, still a postdoc in Cambridge, we wrote a couple of papers about the secure composition of insecure components. And the idea here was to look at secure environments, to look at how you can encapsulate some untrusted piece of code in a way that lets one, with some wrapper, control its interactions with the outside world, and moreover, in a way that you can state and prove some security properties about that. So that motivation is still good, indeed, probably much stronger now than it was then. In that sense, we were ahead of our time. How did we go about it? Well, we say in the paper, to express and reason about wrappers, we need a small programming language. And we proceeded to invent one off the top of our head, a little variant of the pi calculus with some kind of encapsulating boxes. So, I mean, that was probably necessary for us to do anything because that was what we knew. But it was a massive idealization with respect to the kind of encapsulation that happens in practice. And we didn't even, I think, know what real encapsulation mechanisms were like. We didn't know much about operating systems or what have you. We just made this thing up. And that's, in hindsight, makes the results, such as they were here, not all that useful. This was, again, kind of bogus motivation. We probably would have said that we were working on the foundations of computer security. But foundations is a much overloaded term. So people in LICS talked and probably still talk about the foundations of computer science, meaning logic and semantics and type theory and computability and complexity. But then we also have, and people don't talk about this so much using the same words, the foundations of computing as it is practiced out there in the world. And this is Verilog and x86 and ARM and C and C++ and Java and TCP/IP and Linux and Windows, and in general test and debug development and project management and all kinds of things like that. And it is regrettably the case that the foundations of computer science, on the whole, have nothing much to do with the foundations of computing. It would be good if they did. We should try to make it so. Many of us are trying to make it so, but they don't very much. So what that means is, well, that means many things, but one of the things that we have to do if we want to actually target anything in real systems, which you might or might not do, probably statistically, if you're at a workshop attached to LIX, you might not want to do that at all. But if you do want to do that, then you have to do at least one of these. You have to either idealize the system, or you have to restrict the scope of what you're paying attention to something more manageable, or you have to abstract from the system. And these three are quite different from each other. And what we did here was we massively idealized. Right? And if one does that too much, you end up with results that are meaningless, which don't say anything about the system that you're purporting to talk about, or about the problem that you're purporting to talk about. But of course, very often you have to idealize in order to get something manageable. So I'm not saying one shouldn't do that, but I am saying that one should be very clear which of these three things one is doing, and not do them more than you have to, or not do them more than you can without throwing out the baby with the bathwater. Okay, let's move along a bit. So in the early 2000s, a group of colleagues and I did a bunch of work on network protocols. And here the motivation was of a different kind again. Here we saw these existing protocol specifications of TCP protocols and whatnot produced by the IETF, the internet people. These are really vague prose specifications, specification documents. And we asked, can we specify, instead of just giving some vague prose, can we actually define the envelope of allowed behavior of a TCP endpoint precisely with honest maths? Well, I say that's what we said. Actually, the original motivation, which is probably not written in any of these papers, or maybe the first one, is that we'd come from a world of process calculi, and process calculi had mostly assumed a world of non-failing systems. But the essence of distributed systems is that parts of them can fail while the other parts continue. And we wanted better failure semantics to capture that kind of thing. So that was actually why we started doing the work. But it turned out that this was a much better motivation. And this is an important point, right? That very often the reason why you're doing a thing, especially the reason why you start doing a thing, turns out to be quite different from the reason why anybody else should care about it, which is the motivation you actually want to write in the paper at the end of the day. It was kind of a success. We defined in logic, in higher order logic of the whole full system, an envelope of allowed behavior for TCP/IP and the sockets API, and it had clear and experimentally testable relationships to some actual implementations. So we showed that we could cope with the real artifacts without idealization and without much restriction and with just a bit of abstraction. And we learned a lot about doing semantics informed by experiment. And we learned a lot about testing and a lot about working at scale. So the definition of that envelope is something like something like a 9,000 line definition in higher order logic, which is bigger than one normally attempts with pencil and paper maths. And you need to treat it in different ways than you do pencil and paper maths. And it was a success in other ways. We published it in systems papers, and we worked a lot with systems researchers, and that was all very interesting. But it was a failure in that we didn't produce a turnkey system that systems engineers could use that was actually something usable by practitioners. We wanted to do that, but we just ran out of time and effort. So the lead postdoc on the project was Keith Wansborough. He moved off to a job someplace else. I got distracted with other things. Steve Bishop, who was a research assistant on the project, he went off and got a job. Actually, he became a medical doctor and then an anaesthetist. Other people left. We just didn't have the energy or the resource to push this towards the standards bodies or towards real practical uptake. So that's a shame. And we didn't get to the point either of proving substantial theorems. So you have these great big definitions, and that does mean they're very hard to prove things about. But we wanted to prove quite non-trivial facts. For example, that the discrete protocol that is TCP actually is something that, that the congestion control of that protocol is within a class of congestion control algorithms that actually gives you some network stability properties. Right? That would be a lovely thing to prove. It's probably doable with only 1 or 2 PhDs worth of proof. And we didn't really do, we weren't aiming here to do elegant mathematics, and we didn't end up with it. We ended up with workable mathematics. That testing process did a lot of proof inside hole 4 that particular traces were admissible by the spec. And we did prove some theorems about the whole spec, but they were pretty light-hearted. Something to note for anything like this is that, and in some sense it's a positive thing, that there are some kind of fundamental aspects to TCP. There are some subtleties of the protocol that are there for real solid engineering reasons that determine whether it works at all. But then there's also a whole lot of contingent complexity from the historical accidents and mistakes and just random design choices. And one might think as a theorist that one wants to focus only on the first part. But if one wants to speak about the real systems, then both of these become equally important, and one has to somehow tackle both of them at once. It was a crazy amount of work, like 9 person years for the main part, maybe. Maybe it was stupid for us to embark on this as a bunch of postdocs. None of those people had, tenured appointments at the time. But then, well, maybe one has to be optimistic to, start getting anything done in research. It certainly needed a great team, right? So this is not at all a one-man exercise or a one-person exercise. Right here, I think 4 of these people worked maybe 2/3 of their time for a couple of years. And then another thing that might not be obvious is that somehow one needs, if doing this kind of thing, to be able to partition it into publishable units. And the danger here is not that you end up with something that's less than a minimal publishable unit. The danger is that you end up with things that are bigger than maximal publishable units, and that you can't possibly describe within one paper. One can't possibly get across to your readership. So these are not papers that have, one simple idea, which is the kind of thing that at least Popple reviewers love to see. Instead, they're papers that have a bunch of ideas in the service of achieving some goal. It also needs enough security of funding, right? So it turns out to be relatively easy to justify this kind of work, but it would be foolish to jump all the way into the deepest water of some very complex protocol or other system without both an incremental path to publishing it and enough funding for at least the first couple of steps. Okay, let's move along a bit. So after that, a different group of colleagues and I embarked on a whole line of work looking at relaxed memory. And the first substantial paper we published was in Popple 2009, and then there have been a whole bunch of them since then. And the question here was to ask, what is the semantic, well, the retrospective motivation is to ask, what is the semantics of real shared memory concurrency? And there'd been a whole lot of, concurrency theory literature up to that point for 30 years or more, but almost all of it had assumed either a simple interleaving model, sequential consistency, or some message passing abstraction. And those are both good in some circumstances, but they're not what actual shared memory hardware gives you. And in fact, the original true motivation was that Susmit Sarkar, who was a new postdoc in Cambridge at the time, and we wanted to do, we were looking for a new project to do, and we wanted to try verification of the Zen hypervisor, which was at that time a new hypervisor. It was invented by our friends just down the hall in the Cambridge Systems group. But as soon as we looked, we realized that the concurrency semantics that you get from x86 was very unclear. So there had been a bunch of work on other relaxed memory for all kinds of things. There's lots of stuff just before that on Java and also for other hardware architectures. But at that time, the semantics for x86 and IBM Power and C and C++ was all very uncertain. It pretty quickly became a problem that this was sort of a real industry problem, right? At the heart of the industry, where computer architectures hit Linux kernel developers and so on, people just didn't really have a clear view of what the semantics of actual systems was. And this was a case where a bit of semantics, and not too much semantics, could really help practice. So how do we go about it? So we learned here a lot from this previous network semantics project, right? So I said, it didn't have any impact on the world. It didn't have any impact directly on the networking world, as far as I know, although maybe some people have learned some things from some of these papers. If anyone wants to read anything about this, by the way, you should not read this SIGCOMM paper, which was a network-oriented thing partway through the project. One should read this more recent JCM overview of the whole thing. Anyway, we learned a lot from that. Right? We knew already that just doing paper and pencil maths would never be workable for this kind of thing, and that we needed to make semantic definitions that you can execute, not just to execute as code, but to execute as test oracles. So giving some semantics and given some example, you could compute the set of all behavior allowed by that example. And we knew we needed to be able to do experimental testing of hardware to see what it actually does and to compare that against what our semantics did. And that's, I think, one previous piece of work in relaxed memory had done that, but most of them had not done that. Right? They'd taken a more paper maths viewpoint. And then we needed also a bunch of interesting test cases, both a bunch of handwritten tests and a bunch of auto-generated tests to explore these relationships between the model and the actual hardware behavior. And we started off thinking that we were going to be formalizing some abstraction that industry already basically understood. And after a while, it became clear that, well, many aspects were very well understood by the architects and the language implementers and so on. Actually, we needed to co-invent some precise abstraction with them, right? With the systems input and the mathematical input coming together. Again, this needed a great team, and lots of people have worked on this. And this is just the list of authors involved in model design from these papers that I've personally been a co-author on. And many of these people have gone off to do lots of great stuff without me in any way. So Francesco has, and Scott has, and Jad has done an enormous amount, partly with Luke. Batty has in a different direction. Lots of these people have gone on to work in this subject. But so you wouldn't at all embark on a project that needed all of that many people, right? Even you would embark on something that would produce one good paper. Even this as a first paper, that needed a fairly substantial team, but it was sort of manageable, right? Okay. other things one needs that are maybe less obvious. So just to make contact with the architects and the standards committee members, and to establish credibility with them as people that they should spend their time on, and to learn how to communicate with them, that took a couple of years maybe. We had to learn to understand and respect their concerns, not just ours. We had to learn to translate our maths into their terms, to talk to them in terms of the examples that they understood. You can't just walk into a C++ standards committee and say, here is our model, see the nice first order logic specifications. That doesn't work. And you also have to kind of be humble in the face of reality, humble in the face of engineering reality, because a lot of these things, while it is a bunch of historical accident and a bunch of nasty complexity, there are also a whole bunch of real reasons why things are the way they are. And one can't, one is not in a position to second guess that, certainly not at the beginning. And then to make it work, we also have to do what you might call a proper job, right? Not just make models which are good enough to write papers, but aim to write models which are definitive as well as you can, even though they never end up being definitive. All of these end up being subject to change when you learn more. Was it a success? We haven't invented any concurrency architectures out of thin air, but we have influenced all of these concurrency architectures that people actually use. So the community of people that really works with subtle fine-grained concurrency now routinely uses either these models or models of their general form. And academically, it enabled semantics and verification by a bunch of groups above these more realistic models. We, as it were, went out into the jungle and we brought back something and made it more accessible for that more theoretically minded community. We didn't at all know that that would happen at the start. Well, I guess we did have some sense that it was a real problem in the sense that it mattered to that specific larger community. It was also kind of a failure, right? So we made a lot of mistakes along the way. So this paper, for example, it's mathematically perfectly good. It's a very nice model. It matches pretty well what you would think if you just read the Intel documentation from the time, but that documentation did not give a good picture of how the machines actually behave, and this model is useless. The way that we obtained that model, the approach we took, was fundamental to everything we did later, but the model itself, useless. Lots of work still in progress, so it's not at all finished. That's not exactly a failure. It's still mostly, all of this work is still mostly just whole system semantics, not compositional in any way, except for there is a bunch of work on relaxed memory program logics by like Vafiadis and Dreyer and Ralph Young and these people. That's all very good. But that's definitely a limitation in what we have. And for language level models like C and C++, we don't really know how to do it. Then another thing that's interesting to note is that we started doing this in 2009, but there is no reason why we couldn't have started doing it in 1999 or even 1989. Right? Systems were already, like real systems, were already doing relaxed behavior in those times, and the theory and semantics community, with a few exceptions, had just not noticed. I think I am basically out of time here, but I mentioned very quickly that the two things that I've just been talking about, they were aimed at making existing systems better defined, but one can also look at making the construction of new systems in better ways. And in the Cherry project with Robert Watson and Simon Moore and Peter Neumann and a whole host of others, we have been working to extend existing architectures with hardware support that makes a significant fraction of memory safety violations go away. And this is now being explored by ARM in like an industrial scale prototype. And one can start thinking about the semantics of those and proving properties of those. So this is, in some sense, doing secure encapsulation again, but 20 years later, and we can do logical proofs about the security properties of these full-scale architectures. And this still needs quite a lot of work, but it's not out of reach. Right? It's become doable as a result of various things. I am out of time. Let me wind up. So these collaborations from theory to real systems, they can be fruitful, they can be fun, they can be fascinating, they can also be terribly frustrating, and they can be soul destroying. One can sink in enormous amounts of work and it can become invalidated. So should I say, if you're inclined that way, that you should do such things? Maybe, but you should think very carefully. You know, is it actually a feasible idea? You should be optimistic, but only plausibly optimistic. There is, I think, a golden age for semantics and verification, because it's now become possible to do this kind of thing. And there's clear industry appreciation, not in the mass market, but in important key niches. And I conclude by thanking all of my colleagues and students and postdocs for all of this work. This has not remotely been any kind of one-man band. This has been a whole host of different overlapping collaborations. And that's part of what makes it fun. With that, I think I should stop and we should see if there are questions out there, which I would be happy to answer.